The Zach West electrolyzer. Zach West of the USA has produced a motorcycle electrolyzer. Zach's 250 cubic centimeter motorcycle can run on the output of his electrolyzer, and Zach estimates the output as being 17 liters per minute of HHO gas, which seems to me to be far too high for the current flow. This is not a coefficient of performance greater than 1 system, as the output from the electrical system of the motorcycle is very limited, and so the battery will slowly run down as time goes by. However, Zach's design of electrolyzer is interesting, both for its simplicity and its high rate of gas output. The increased gas volume which would be produced if this design were adapted for, and driven by, a 12-volt input could be very useful, especially if combined with David Query's system, which allows the resulting modified gas to operate in unmodified engines, as shown later on in this chapter. The method which Zach uses is somewhat unusual, as he manages to bleed off and discard most of the oxygen produced. This means that the remaining gas is mainly hydrogen, which is far less reactive than HHO, which is already in the perfect proportions for combination back into water and so is highly reactive. Instead, the resulting gas can be compressed reasonably well, and Zach compresses it to 30 pounds per square inch, in a storage container. This helps with acceleration from stationary at traffic lights. Zach uses a simple, modular style of construction where a series of coiled electrode pairs are each placed inside an individual length of plastic pipe. This is a design which is neither difficult nor particularly expensive to build. In overall broad outline, Zach's electrolyzer is fed water from a water tank to keep it topped up. The electrolyzer box contains several pairs of electrodes which split the water into hydrogen and oxygen when fed with pulsed electrical current generated by the electronics, which is powered by the electrical system of the motorcycle. The gas produced by the electrolyzer is fed to a dual-purpose bubbler, which prevents any accidental igniting of the gases from traveling back to the electrolyzer, and in addition, removes most of the oxygen from the gas by acting as a gas separator. The arrangement is like this: combined bubbler and gas separator. Electromagnet with a steel core. The hydrogen gas output from the electrolyzer is not fed directly to the engine, but instead it goes to a pressure tank which is allowed to build up to 30 pounds per square inch before the engine is started. The majority of the oxygen produced by the electrolysis is vented away through a 30 psi one-way valve which is included to keep the pressure inside the bubbler, and the electrolyzer, at the 30 psi level. That pressure is excessive for a high-performance electrolyzer which produces HHO, which is highly charged electrically and so will ignite spontaneously when compressed, due to its own electrical charge. In this simple DC electrolyzer, the HHO gas is mixed with quite an amount of water vapor which dilutes it and allows some compression. The water supply system operates by having an airtight supply tank positioned at a higher level than the electrolyzer. A small diameter, 1/4 or 6 mm, plastic tube coming from the supply tank feeds through the top of the electrolyzer and straight down, terminating at exactly the electrolyte surface level wanted in each of the electrolyzer tubes. When the electrolysis lowers the electrolyte level below the bottom of the pipe, bubbles of gas pass up the tube, allowing some water to flow from the tank to raise the electrolyte surface level back to its design position. This is a very neat passive system needing no moving parts, electrical supply or electronics, but yet one which accurately controls the electrolyte level. One essential point to understand is that the water tank needs to be rigid so that it will not flex, and the filler cap needs to be airtight to prevent the entire water supply discharging into the electrolyzer. Another point to remember when topping up the water tank is that the tank contains a mix of air and HHO gas above the water surface and not just plain air, and that gas mix is at 30 psi pressure. Now, to cover the design in more detail. This 6-volt electrolyzer contains 8 pairs of electrodes. These electrode pairs are coiled around in Swiss roll style and inserted into a length of 2-inch, 50 mm, diameter plastic pipe, 10 inches, 250 mm, tall. The electrodes are each made from a 10-inch, 250 mm, by 5-inch, 125 mm, of 316L, grade stainless steel shim stock, which is easy to cut and work. Shim stock is available from a local steel supplier or metal fabrication company and is just a sheet of very thin metal. Each electrode is cleaned carefully, and wearing rubber gloves, cross-scored using coarse sandpaper in order to produce a very large number of microscopic mountain peaks on the surface of the metal. This increases the surface area and provides a surface which makes it easier for gas bubbles to break away and rise to the surface. The electrodes are rinsed off with clean water and then coiled round, using spacers to maintain the necessary interplate gap, to form the required shape, which is then inserted into a length of plastic pipe as shown here. Gas vent. Water supply pipe. Polyvinyl chloride pipe. Two 316L grade stainless steel plates wound up into a helix. As the springy metal pushes outwards in an attempt to straighten up again, spacers are used to keep the electrodes evenly separated along their whole length by inserting 1/8 thick vertical spacer strips. The connections to the plates are made by drilling a hole in the corner of the plate and inserting the wire several times through the hole, twisting it back around itself and making a wire-to-wire solder joint on both sides of the steel. The joint is then insulated with silicone or any other suitable material. It is, of course, essential that the joint does not short-circuit to the other electrode even though that electrode is very close by. Drill hole in plate. Clean plate and wrap wire through the hole. Solder the wire on both sides. Insulate with silicone. It is always difficult to make a good electrical connection to stainless steel plates if space is restricted as it is here. In this instance, the electrical wire is wrapped tightly through a drilled hole and then soldered and insulated. The soldering is only on the wire as solder will not attach to stainless steel. An unusual feature of this design is that each of the electrode pairs is effectively a separate electrolyzer in its own right as it is capped top and bottom, and effectively physically isolated from the other electrodes. The water feed comes through the top cap which has a hole drilled in it to allow the gas to escape. The electrical wires, number 12 AWG or SWG14, are fed through the base and sealed against leakage of electrolyte. Each of these units has some electrolyte stored above it, so there is no chance of any part of the electrode surface not being able to generate gas. There is also a large amount of freeboard to contain splashes and sloshing without any being able to escape from the container. The end caps are standard PVC caps available from the supplier of the polyvinyl chloride piping, as is the PVC glue used to seal them to the pipe. 8 of these electrodes are placed in a simple electrolyzer case and connected together in pairs as shown here. Pairs of pipe-enclosed electrode spirals are then connected in a chain inside the electrolyzer as shown here. Many years of experimentation and testing have shown that 316L grade stainless steel is the most suitable material for electrodes, but surprisingly, stainless steel is not highly electrically conductive as you would expect. Each electrode causes a voltage drop of nearly half a volt, and so careful surface preparation, cleansing and conditioning are needed to get top performance from the electrodes. This process is described in detail by the very experienced Bob Boyce, who says, "The preparation of the plates is one of the most important steps in producing an electrolyzer which works well. This is a long task, but it is vital that it is not skimped or hurried in any way. Surprisingly, brand new shiny stainless steel is not particularly suitable for use in an electrolyzer and it needs to receive careful treatment and preparation before it will produce the expected level of gas output. The first step is to treat both surfaces of every plate to encourage gas bubbles to break away from the surface of the plate. This could be done by grit blasting, but if that method is chosen, great care must be taken that the grit used does not contaminate the plates. Stainless steel is not cheap, and if you get grit blasting wrong, then the plates will be useless as far as electrolysis is concerned. A safe method is to score the plate surface with coarse sandpaper. This is done in 2 different directions to produce a crosshatch pattern. This produces microscopic sharp peaks and valleys on the surface of the plate, and those sharp points and ridges are ideal for helping bubbles to form and break free of the plate. When doing hand sanding, the sandpaper is drawn across the plates in one direction only and not backwards and forwards, as the backward stroke always destroys the perfectly good ridges created on the forward stroke. Also, You only need 2 strokes in one direction before turning the plate through 90 degrees and completing the sanding of that face of the plate with just 2 more strokes, again, with no backstroke. Always wear rubber gloves when handling the plates to avoid getting finger marks on the plates. Wearing these gloves is very important as the plates must be kept as clean and as grease-free as possible, ready for the next stages of their preparation. Any particles created by the sanding process should now be washed off the plates. This can be done with clean tap water, not city water though, due to all the chlorine and other chemicals added, but only use distilled water for the final rinse. While potassium hydroxide, KOH, and sodium hydroxide, NaOH, are the very best electrolytes, they need to be treated with care. The handling for each is the same, always store it in a sturdy airtight container which is clearly labeled danger. Potassium hydroxide. Keep the container in a safe place, where it can't be reached by children, pets or people who won't take any notice of the label. If your supply of KOH is delivered in a strong plastic bag, then once you open the bag, you should transfer all its contents to sturdy, airtight, plastic storage containers, which you can open and close without risking spilling the contents. Hardware stores sell large plastic buckets with airtight lids that can be used for this purpose. When working with dry KOH flakes or granules, wear safety goggles, rubber gloves, a long-sleeved shirt, socks and long trousers. Also, don't wear your favorite clothes when handling KOH solution as it is not the best thing to get on clothes. It is also no harm to wear a face mask which covers your mouth and nose. If you are mixing solid KOH with water, always add the KOH to the water, and not the other way round, and use a plastic container for the mixing, preferably one which has double the capacity of the finished mixture. The mixing should be done in a well-ventilated area which is not drafty as air currents can blow the dry KOH around. When mixing the electrolyte, never use warm water. The water should be cool because the chemical reaction between the water and the KOH generates a good deal of heat. If possible, place the mixing container in a larger container filled with cold water, as that will help to keep the temperature down, and if your mixture should boil over it will contain the spillage. Add only a small amount of KOH at a time, stirring continuously, and if you stop stirring for any reason, put the lids back on all containers. If, in spite of all precautions, you get some potassium hydroxide solution on your skin, wash it off with plenty of running cold water and apply some vinegar to the skin. Vinegar is acidic, and will help balance out the alkalinity of the potassium hydroxide. You can use lemon juice if you don't have vinegar to hand, but it is always recommended to keep a bottle of vinegar handy. Plate cleansing is always done with sodium hydroxide. Prepare a 5% to 10%, by weight, sodium hydroxide solution and let it cool down. A 5% solution by weight is 50 grams of sodium hydroxide in 950 cubic centimeters of water. A 10% solution by weight is 100 grams of sodium hydroxide in 900 cubic centimeters of water. As mentioned before, never handle the plates with your bare hands, but always use clean rubber gloves. A voltage is now applied across the whole set of plates by attaching the leads to the outermost 2 plates. This voltage should be at least 2 volts per cell, but it should not exceed 2.5 volts per cell. Maintain this voltage across the set of plates for several hours at a time. The current is likely to be 4 amps or more. As this process continues, the boiling action will loosen particles from the pores and surfaces of the metal. This process produces HHO gas, so it is very important that the gas is not allowed to collect anywhere indoors, such as on ceilings. After several hours, disconnect the electrical supply and pour the electrolyte solution into a container. Rinse out the cells thoroughly with distilled water. Filter the dilute sodium hydroxide solution through paper towels or coffee filters to remove the particles. Pour the dilute solution back into the cells and repeat this cleaning process. You may have to repeat the electrolysis and rinsing process many times before the plates stop putting out particles into the solution. If you wish, you can use a new sodium hydroxide solution each time you cleanse, but please understand that you can go through a lot of solution just in this cleaning stage if you choose to do it that way. When cleansing is finished, typically 3 days of cleansing, do a final rinse with clean distilled water. It is very important that during cleansing, during conditioning and during use, that the polarity of the electrical power is always the same. In other words, don't swap the battery connections over, as that destroys all the preparation work and requires the cleansing and conditioning processes to be carried out all over again. Using the same concentration of solution as in cleansing, fill the cells with dilute solution. Apply about 2 volts per cell and allow the unit to run. Remember that very good ventilation is essential during this process. As water is consumed, the levels will drop. Once the cells stabilize, monitor the current draw. If the current draw is fairly stable, continue with this conditioning phase continuously for 2 to 3 days, adding just enough distilled water to replace what is consumed. If the solution changes color or develops a layer of crud on the surface of the electrolyte, then the electrodes need more cleansing stages. After 2 to 3 days of runtime, pour out the dilute potassium hydroxide solution and rinse out the cells thoroughly with distilled water. The construction which Zach has used is very sensible, utilizing readily available, low-cost polyvinyl chloride piping. The spiral electrodes are inside 2-diameter pipe, and Zach says that the bubbler is also 2-diameter polyvinyl chloride pipe. I seriously doubt that a 2-inch diameter bubbler could handle a flow as high as 17 lpm, which is a substantial amount. Also, you want the bubbles in the bubbler to be small in order that the gas comes into good contact with the water. Consequently, using more than one bubbler where the diagram shows just one, would be sensible. At this time, Zach only uses one bubbler, but a second one is highly desirable, located between the storage tank and the engine and positioned as close to the engine as possible. This extra bubbler does 2 things. Most importantly, it prevents the gas in the storage tank being ignited by a backfire caused by a valve sticking slightly open, and secondly, it removes every last trace of potassium hydroxide fumes from the gas, protecting the life of the engine. This is a big gain for such a simple addition. The gas storage tank is also made from polyvinyl chloride pipe, this time, 4-inch, 100 mm, diameter, 14 inches, 350 mm, long, with standard end caps fixed in place with polyvinyl chloride glue as shown below. This is a compact and effective arrangement well suited for use on a motorcycle. The majority of this extra equipment can be mounted in bike panniers, which is a neat arrangement. The electric drive to the electrolyzer is from a pulse width modulator, DC motor speed controller, which was bought from the Hydrogen Garage, as Zach is in America. That particular pulse width modulation board is no longer available, so especially for those people in Europe the choice might be roomcybernetics.com, although there are many suppliers and the module should not be expensive. As this unit was rated at just 15 amps maximum, Zach added another 15 amp rated FET transistor in parallel to the output stage to raise the current capacity to 30 amps. A fuse protects against accidental short circuits, and a relay is used to control when the electrolyzer is to be producing gas. The connecting wire is number 12 AWG, SWG14, which has a maximum continuous current capacity of just under 10 amps, so although the current peaks may be 20 amps, the average current is much lower than that. 2 electromagnets outside the bubbler, positioned 2.5 inches, 65 mm, above the base, are connected as part of the electrical supply to the electrolyzer, and these cause most of the oxygen and hydrogen bubbles to separate and exit the bubbler through different pipes. There is a divider across the bubbler to assist in keeping the gases from mixing again above the water surface. The bubbler also washes most of the potassium hydroxide fumes out of the gas as the bubbles rise to the surface, protecting the engine, as these fumes have a very destructive effect on engines. The objective with any HHO system is to have the minimum amount of gas between the bubbler and the engine in order to block the ignition of the gas in the unlikely event of a backfire. In this system, the gas storage tank contains a very large amount of gas, though admittedly it is not full HHO gas thanks to the electromagnet separation system, but nevertheless, it would be most advisable to have a second bubbler between the gas storage tank and the engine, positioned as close to the engine as possible. HHO gas produces a very high-speed shock wave when it is ignited, so the bubbler needs to be of strong construction to withstand this. No pop-off bubbler cap or blowout device acts fast enough to contain a HHO shock wave, so make the bubbler housing strong enough to withstand the pressure wave. ZAC's electrolyser arrangement is like this. Spiral wound electrodes. Combined bubbler and gas separator. It must be realized that the water tank, electrolyser, bubbler separator and hydrogen holding tank, all operate at 30 pounds per square inch. This means that each of these containers must be robust enough to withstand that pressure quite easily. It also means that the 30 psi one-way check valve on the oxygen venting pipe is an essential part of the design as well as being a safety feature. As a bubble of gas from the electrolyser escapes into the water tank every time a drop of water feeds to the electrolyser, the contents of the water tank above the water surface becomes a stronger and stronger mix of air and HHO. Consequently, it soon becomes an energetic mixture. It is common for static electricity to build up on a tank of this nature, so it will be very important to earth both the tank and its cap before removing the cap to top up the tank with more water. The electrolyser has a potassium hydroxide, KOH, solution in it. The electrolysis process produces a mixture of hydrogen, oxygen, dissolved gases, air, and potassium hydroxide fumes. When the system is being used, the water in the bubbler washes out most of the potassium hydroxide fumes, and in doing so, it gradually becomes a dilute electrolyte itself. Potassium hydroxide is a true catalyst, and while it promotes the electrolysis process, it does not get used up during electrolysis. The only loss is to the bubbler. Standard practice is to pour the contents of the bubbler into the electrolyser from time to time, filling the bubbler again with fresh water. Potassium hydroxide has been found to be the most effective catalyst for electrolysis, but it has a very bad effect on the engine if it is allowed to enter it. The first bubbler is very effective in removing the potassium hydroxide fumes, but many people prefer to take the scrubbing process a step further by placing a second bubbler in the line, in this instance, between the hydrogen pressure tank and the engine. With two bubblers, absolutely no potassium hydroxide fumes reach the engine. When running with HHO gas as the only fuel, it is essential to adjust the timing of the spark so that it occurs after top dead center. The timing on this bike is now set at 8 degrees after top dead center. However, if David Quirie's style of bubbling the HHO through a liquid such as acetone, then no timing alterations would be needed. This electrolyser is designed to run off the nominal 6 volts of a motorcycle electrics, about 7.3 volts with the engine running, but increasing the number of tubes, each containing electrode coils, would convert the design to a 12-volt system, and then the electrolyser housing would probably be like this. It is possible that 7 sets of 3 or 4 spirals wired in parallel would be used for larger engines with their 13.8-volt electric systems. ZAC uses the very simple method of allowing excess gas to be vented via the oxygen valve if gas production exceeds the requirements of the engine. When operating on a 12-volt system, it might be more convenient to use a standard pressure switch which opens an electrical connection when the gas pressure rises above the value for that switch. The pressure switch just mounts on one of the end caps of the pressure tank, and the switch electrical connection is placed between the relay and the electrolyser. If the gas pressure reaches its maximum value of 30 psi, then the switch opens, stopping electrolysis until the pressure drops again. An electrolyser should not be considered as an isolated device. You need to remember that both electrical and gas safety devices are an essential part of any such installation. The electrical safety devices are a circuit breaker, as used by any electrician when wiring a house, to protect against accidental short circuits, and a relay to make sure that the booster does not operate when the engine is not running. However, the system designed by ZAC West is almost certainly not self-sustaining, and if that is correct, then the battery powering the electrolyzer will need to be charged between trips. That does not have to be the situation, as high-efficiency electrolyzers are available. First, the Shigeta Hospi spiral plate electrolyzer, shown on page 719 of the appendix, has produced 7 lpm of HHO gas mix for an input of just 84 watts, and while that 84 watts is an inconvenient 2.8 volts at 30 amps, it should be possible to raise the voltage and lower the current without losing too much of the performance. In my opinion, the electrics of a motorcycle should be able to output 84 watts, and so the motorcycle could become self-powered. Motorcycles can definitely become self-powered, as can be seen from the electric motorcycle system of Teruo Kawai's coefficient of performance greater than 3 design shown in Chapter 2. Teruo went to America and was in a meeting aimed at getting his design manufactured and sold in America when the meeting was interrupted and Teruo intimidated into abandoning his venture. You must also remember that Steve Ryan of New Zealand demonstrated running his motorcycle on treated water. I suspect that the treated water was water which had been infused by charged water clusters, as described by Surratt and Gorley later in this chapter. Their electrolyzer has an efficiency of 0.00028 kWh or less to generate 1 liter of gas. Those inconvenient units mean that to produce 1 lpm needs 16.8 watts or 7 lpm needs 118 watts. If cold water mist is added to the air entering the motorcycle engine, then it seems likely that a good deal less than 7 lpm would be needed. If you have a good enough tank which is made of a material capable of containing the very small molecules of this gas, then the gas can be compressed to 1000 psi, and that should allow a motorcycle to run for some time on the gas cylinder. The duplex booster designed by Bill Williams. A fully submerged design from Bill Williams in the USA is another different style of booster. The construction details for this booster design can be downloaded free from the web using the link http://www.freeenergydevices.com/duplex.pdf. There are many other designs, including those with concentric pipes, each having its own advantages and disadvantages, some being commercially available as ready-made devices, and there are links to these boosters on the websites mentioned above and a general booster forum at http://tech.groups.yahoo.com/group/watercar. And another at http://tech.groups.yahoo.com/group/hho, where people will answer any queries. One problem with the use of boosters is that if the HHO gas volume is higher than it needs to be, the vehicle's electronic control unit, ECU, is liable to detect the improved fuel burn and start pumping in excess fuel to offset the improved conditions. How to deal with this situation is covered in the free document, which can be downloaded from http://www.freeenergydevices.com/d17.pdf. The Hog electrolyzer from Selwyn Harris. An interesting design is the Hog electrolyzer as described by Selwyn Harris of Australia. The Hog cell has 2 stainless steel mesh electrodes coiled around each other. This gives a large electrode surface area in a very compact container. In this version of the design there are 6 identical cells which feed into a large bubbler. For clarity, only 2 of the 6 electrolyzer cells are shown here. The items marked with a blue dot form just one of 3 identical sets. That is, 3 filters feed out from the bottom of the bubbler, the flow through them being caused by 3 separate pumps, and the 2 electrolyzer cells marked 1 and 2 along with their associated pipes and 4 one-way valves, are replicated to give electrolysis cells 3 to 6, which are not shown in this diagram. Those 3 identical sets are connected to the central bubbler, spaced around it evenly at 120-degree positions horizontally as shown in rough outline here. The water is circulated through the set of cells using 3 small pumps, and there are 2 water collectors built onto the bottom of the bubbler. Also, as the electrolyte used is rainwater, and each electrolysis cell is completely full of electrolyte, as this is an electrolyte circulation style of electrolyzer. Each of the 3 pumps has its own filter to trap any particles coming from the cells, as experience has shown that the water can contain a considerable amount of material. The filters are standard irrigation inline filters made from transparent plastic filled for 3/4 of their length with fine plastic sponge material. A key feature of the cell design is the use of 2 powerful neodymium magnets per cell. These act directly on the water, and that causes a major increase in the gas production rate. The magnets have their north poles facing towards each other. The 2 mesh electrodes are made from stainless steel wire of 0.32 mm diameter and woven to give 2 mm holes between the wires and a 0.65 mm overall sheet thickness. These dimensions are important as other mesh sizes and styles do not give so good a performance. The electrodes are wider at one end to form a connection tab which allows easy electrical connection to each electrode, and they are then wired in parallel so that each cell gets 12 volts across it as shown here. The 2 mesh electrodes are cut like this. And the mesh material looks like this. The 6 electrolyser cells and the single large bubbler are constructed using standard plastic plumbing materials. Piece of 50 mm diameter plastic pipe. Pipe collar. Neodymium magnet, outer diameter 40 mm, inner diameter 15 mm. Magnet support disc. Piece of 50 mm diameter plastic pipe. Pipe collar. Neodymium magnet, outer diameter 40 mm, inner diameter 15 mm. Magnet support disc. Piece of 50 mm diameter plastic pipe. End cap. The connecting pipes are a clear plastic, heat-tolerant type of 12 mm, 0.5, diameter. The bubbler is also constructed from plastic pipe fittings. Splash protection pumice or fiber pot scrubber material. As some people have difficulty in visualizing the way in which the electrodes are combined, this simplified concept sketch may be helpful. The 2 electrodes are kept separated by the use of small diameter fiber washers held in place between them at strategic places using super glue. The mesh itself is then treated by being immersed in citric acid in order to make it work well with rainwater. There are 3 of these pairs of electrolyser cells, each pair being connected to the upper collector reservoir. The water being pumped out of each cell is passed through one of the 3 filters before entering the collector reservoir, which feeds the small pump which keeps the water circulating, which in turn keeps removing any particles which have got into the rainwater. When used with rainwater from a barrel, this electrolyser is said to draw just 1.4 amps per cell, giving a total input of about 115 watts when run on a 12-volt electrical supply. While rainwater is supposedly pure, the reality is that it seldom is, and its ability to carry a current varies dramatically from place to place and even more widely from country to country. If you decide to build this electrolyser and find that you do not get anything like 1.4 amps flowing through any one cell, then you may well have to add a small amount of electrolyte to the water in order to get the current flowing. That is, assuming that you want a current flow of 1.4 amps per cell on 12 volts. The output of this electrolyser is said to be capable of running a small electrical generator, but that has not been confirmed at this time. Ava Magnetic Levitation's electrolyser. Adam of Ava Magnetics shows a very nicely constructed electrolyser based on an entirely different style of electrode. His video is at https://www.youtube.com, and his cell looks like this. Initially built using stainless steel pipe, the electrical resistance of the long coil proved to be a problem, so Adam overcame the problem by inserting copper pipe inside the stainless steel pipe. Copper carries electrical current very well, while stainless steel has quite a high resistance to current flow, which many people find very strange, having been taught in school that all metals conduct electricity. In a coil like this, electric current has to pass through a considerable length of stainless steel in order to reach the lower turns, and that resistance to current flow is greater than the situation with an electrolyser which uses stainless steel sheets. The copper tube down the inside of the steel pipe makes a major difference because the current flows easily through the copper, and then at every point along the tube, the current only needs to flow sideways through a thin layer of stainless steel in order to perform the electrolysis. The photograph above looks like a very neatly wound coil with 12 turns in it. That is not the case. It is 2 separate coils with turns 1, 3, 5, etc. being in one coil and turns 2, 4, 6, etc. being in the other coil. That arrangement means that each turn in the coil has a turn with the opposite voltage beside it, and the electrolysis takes place between adjacent turns in the coil. The ends of each coil are sealed off carefully to prevent corrosion of the copper pipe by the electrolyte being used. Unfortunately, most of the surface area of the circular pipe electrode is not close to its neighboring coil surface, and that increased distance reduces the rate of gas production for those areas. I suspect that Adam is using a fairly dilute electrolyte in order to keep the heating effect under control, and so, better performance may result when using full-strength electrolyte. However, the HHO production at around 16 amps looks impressive, as shown here just before the whole container is obscured by the HHO bubbles coming off the coils. At full power, the cell draws 18 amps when powered through a pulse width modulator manufactured by the HHO Power Cell Company using a battery of around 12.5 volts. That 225 watts produces a gas output rate which needs to be measured. In my opinion, the gas output pipe needs to be much larger, with an inner diameter of perhaps 15 mm, as a small pipe hinders the escaping gas. If you don't believe that, then try blowing through a length of 6 mm diameter plastic pipe and see how hard that is to do. Nevertheless, this is a simple, basic electrolyzer with just 2 electrodes, although, possibly because the pulse width modulator is feeding it a good quality square wave signal, the small bubble size suggests that there is an efficiency gain which makes it perform better than would be expected. A single cell like this will find it hard to escape from the basic fact that 1.24 volts is all that is used in water electrolysis, and even with the voltage drop across stainless steel, you really do not want more than 2 volts between the plates. In other words, only 2 volts of the battery's 12 volts can actually make gas, and so, the vast majority of that 225 watts goes to make heat and not gas. The situation for 1, 2 or 3 single cells is like this. It is probable that HHO production at 225 watts would be doubled if 2 of these cells are connected in series, that is, connected in a chain. The performance would probably be tripled at that same 18 amps of current, if 3 of these cells are connected in series across the voltage source. If that is done, then ideally, each cell needs to be inside its own separate container. Adam suggests that the coil produces a magnetic field which boosts the production of HHO, and considering the effect of the magnets in the Shigeta-Hospi cell, he may well be right. The arrangement with 3 cells connected in series and powered through a frequency-adjustable pulse width modulator would be like this, although the gas outlet pipes need to be connected together with short pipe connections, as those pipes will be filled with energetic HHO when in use. As always, the battery connects to a circuit breaker CB or fuse before anything else is connected. The pulse width modulator PWM is effectively like Dave Lawton's most simple circuit with adjustable frequency, adjustable mark space ratio, or duty cycle as it is sometimes called, and a high output current capability. The electrical connections to the cells are done as shown in the diagram, and the cells are all positioned the same way round, as that allows testing with the cells leads swapped over to see if that makes a difference when the best frequency and duty cycle have been found. Please remember that a bubbler is essential on the gas output pipe, and the depth of water in any bubbler should be at least 5 inches, which is 125 millimeters. No measurement of the rate of HHO flow has been made. This can be measured with a cheap gas flow meter from a medical equipment supplier, or a result which is easily good enough for our purposes can be determined by using a 2-liter or other suitable container of known capacity, filling it with water and bubbling the HHO output into the container as shown here. The result using this method is got by timing how long it takes for the bottle to be filled with the HHO gas mixture, and from that, working out how many liters are being produced per minute. For example, if it takes 1 minute to fill a 2-liter bottle, then the flow rate is 2 liters per minute. If it takes 2 minutes to fill, then the gas output rate is 1 liter per minute. If it takes 2 minutes and 30 seconds to fill, then the rate is 0.8 liters per minute. The result will be altered slightly by the atmospheric pressure, which changes from hour to hour, but we only need a rough estimate, especially if we are just comparing performance after some small change to the method of electrolysis. The https://www.youtube.com video shows methods of winding pipes into helical coils as used here and the plastic spacers needed, but the man posting, ANNMANN, has a fully equipped workshop and constructional skills not available to most experimenters. Unfortunately, he does not seem to aware of the fact that electrodes need to be very close together for the best HHO production. He has tried using marine cable, used for mast stays, instead of pipe, and that is, of course, very much easier to use when making spiral electrodes, but it is probable that 4 spacers would be needed rather than just the 2 used with pipe spirals. There is also no scope for using copper inside the hawser. Selwyn Harris of Australia, who is a very experienced HHO user, states that it is very difficult to wind stainless steel pipe into an accurate spiral. He wonders if winding the spirals using copper pipe, which is very much easier to bend than stainless steel, and then electroplating the spiral with chromium, might not be a better and more practical way of producing good working spiral electrodes. For me, with my serious lack of accurate constructional skills, another much easier method of construction occurs to me. First, the arrangement of 2 spirals is not really effective for electrolysis as shown here. The rate of electrolysis is directly proportional to the area of the electrodes. It is also highly affected by the separation of the electrodes. With the wires or pipes shown on the left, only a small percentage of the surface area is spaced at the best distance which your construction allows, marked by the red arrows. The 2 plate electrodes shown on the right have their entire surface area at the optimum spacing. So, if we are going to use pipes or wires, then we want to increase the most active surface area, and in fact, increase the electrode area overall. Working with steel is much more difficult than working with plastic, especially since most of us do not have the tools, workspace and skills to help us succeed. Using marine-grade stainless steel cable is a very appealing option. This material is shown at https://www.youtube.com and looks like this. It is available from ships chandleries worldwide and is constructed from stainless steel wires. If we use this, then we have to accept the fact that its electrical resistance will be high, but the big advantage is that we only have to make the plastic spacers. This brings us to the problem of increasing the surface area and decreasing the gaps between the wires. While ANNMANN has excellent video presentations, please do not be misled by the excessively large gaps which he had between his wires. The largest gap that we want is 3 mm, and ideally, we would like 2 mm gaps. So, for this I suggest that a plastic plate is drilled like this. For this, the hole size matches your cable diameter, say, 6 mm, and the gaps between the holes are 2 mm if you are confident, and 2.5 or 3 mm if you are not confident of your skill in drilling plastic. This plate will be used to wind 4 nested spirals. As the cable is flexible, we need to use 2 additional spacer strips like this. These are to make sure that the desired gap is maintained along all of the cable length, by threading the cable through these as each turn is made. That way, the cable is supported every quarter turn, maintaining the gap size all the way around every turn. Although only one type of cable is used, colors are used in the following diagrams merely to make it easier to see where the turns in each winding start and finish. All windings start at the bottom and end at the top. The first winding uses the innermost holes. This winding is made with 2 separate lengths of cable, one shown in green and one shown in red. The lower end of the red cable terminates just this side of the plastic sheet. The lower end of the green cable terminates just beyond the other side of the plastic sheet. Unlike the diagram, the cable is not cut off short as shown but is left long so that it can be connected outside the plastic cell container. We now double the electrode surface area by winding a second pair of coils just outside the first one. The arrangement looks like this. This second layer is wound in exactly the same way as the previous one. The outer cable turns are not exactly above the spiral turns underneath, but they are very close to being directly above. When we connect the cables electrically, we arrange for the cables surrounding any cable to be the opposite polarity, so that the electrolysis is maximized. The next step is to wind the third layer. And then the fourth layer is wound using the remaining holes. Connected electrically as shown, every cable in the first and fourth layers is surrounded on three sides with cables of opposing polarity. The cables in layers 2 and 3 have every turn surrounded on all four sides by cables of the opposing polarity. So, this arrangement has overcome the need for difficult pipe bending, has increased the electrode area considerably and has achieved a reasonable gap between the electrodes and has improved the area of best electrolysis by 87%. We now improve matters considerably by using 3 of these cells in series in order to use the applied power more efficiently. There is, of course, no reason why there should not be more than 3 of these cells in series, and I would expect 5 to be the likely maximum due to excessive voltage drop across the stainless steel cable. There is also no reason why there should not be 5 or more spiral layers in each cell, and each additional layer raises the overall efficiency of that set of spirals. However, while it seems very probable that this construction would yield a good performance, please remember that this is only a suggestion and at time of writing, it has not been built and tested. When first testing the unit, the pulse width modulator is set to give a low to medium current flow through the cells. Then the frequency control is used to get the maximum gas output without altering the current setting. If the current drops at the point of peak gas production during this test, that is not a problem. With multi-layer spirals of this type, a gas outlet pipe of 20 mm would be recommended. Also, the gas outlet should have a baffle plate across it to prevent tiny droplets of electrolyte escaping with the gas, as shown elsewhere in this chapter. That should be done even if the electrolyser is to be used in a stationary location such as feeding a generator. Electrical connections to the ends of the spiral wires can be made with large screw connectors, not unlike the ordinary hardware store type but intended for much larger wires. These are also available through ship's chandlers, as boats often use high current 12-volt wiring of large diameter.